Okay, so now let's look at different forms of energy. What are the different types of energy? So remember when we did forces, like I said, energy is a different way to analyze motion. And the original way when we did forces, the first thing to understand is what are the different types of forces? And we need to be able to tabulate all the forces on something before we can talk about what will happen to its motion. We're going to do a very similar thing. So we need to know what are all the types of energy there is. And I'm going to list a bunch of them so to give you an idea of what they are. But believe it or not, the rest of the course, pretty much, we're only going to look at two energies. And that's going to be all that is enough to analyze motion. So don't be intimidated by a list because in the real life, there's a lot of forms of energy. But the rest of 3A, there's only going to be two that we're going to deal with 90% of the time. Okay, so the first type is kinetic energy, which I already said in my definition. And to give a rough, the rigorous definition is what is kinetic energy is its mass times its speed squared divided by 2. That's the definition, right? You can't get more rigorous than that. That's the most formal. But just to get a feeling, so I'm not going to write a double dot, right? It's not necessarily a definition, but the intuitive idea is the energy of motion, right? You can see from the definition, half mv squared, right? So I'll put it in brackets, right? Let's write it more formally with the equal sign. So kinetic energy. Yeah, let's do KE. It doesn't matter. If you're lazy, just do K, whatever. Okay. So you see, when will you have kinetic energy? The key bit is speed. If you have speed, you have kinetic energy. So it's the energy of motion. If you're moving, you have kinetic energy, unless you don't have mass. Right? Good. So that is the first type. What other energies can you think? What energies? Remember how I define energy is, well, you can define it as the ability to do work, but I define it as the ability to change that number. Well, you know that if nothing in the force approach, if no force is applied to it, V will stay constant, right? So it will never change. So it's a similar idea. If you don't have any energy that is going to add to the system, so if my system is a box moving in space, right, or an apple moving in space, it's going to move forever unless I inject some new energy into it or remove some energy, right? But energy cannot be created or destroyed. So I'll need to find some ways some other source to give it energy, or if I remove it, I need to transform some of its kinetic energy into something else. What can you provide energy to make something move faster, right? To change its motion, to change its kinetic energy? Well, there is chemical energy. So you can create a chemical reaction, and it'll push things through. And the typical thing is, for example, a battery. Right, a battery cell, just a dry battery. If you go to Walmart, buy a battery, that's going to push the electrons around the circuit, right? How does or any chemical reaction, in some sense, your car, the internal combustion engine of your vehicle, is a chemical energy that is stored in the chemicals, which is fuel, right? In the gas, in the gasoline. So the stored energy. Notice we're not. This is why physics is so much easier than engineering. In engineering, you have to worry about how you take that energy and transform it into kinetic energy. Right? You have fuel. How do you make that into motion so that the car will move? We're not going to worry about that. We're just going to worry that we're not going to worry about the details of how that happened. We're going to look at a macroscopic picture. It is possible to happen, right? Because you store a certain amount of chemical energy. We're not going to worry that we'll leave it to the engineers to figure out how that engineering process works. But we'll be able to calculate if you store that amount of energy in the chemicals, this is how much you can change the kinetic energy. You can make it go from how fast to how fast, right? So yeah, this is the energy stored in chemicals. So I said battery because battery is also basically chemicals, but chemical solution, but copper and zinc on both sides. It will create energy to push electrons around. So you can think of it can change kinetic energy. Okay. And then sometimes we are slightly more specific. The energy stored in battery, we call it electrical energy. So this is energy stored in an electric circuit or electric fields. Stored in electric circuits or electric fields. Now, we haven't talked about circuits and electric fields yet, but that's the topic basically you look at in 3B. Okay, so you see what I mean is we're going to talk about two specific energy, kinetic energy and one more. And then the rest of the physics 3 series, in some sense, is looking at different types of energy. You won't even touch chemical energy, but that is the part of chemistry, right? And potentially one more, we might touch on this a little bit, is elastic energy or elastic potential energy, right? So I'll give it the full name, elastic potential energy. And this is the energy stored in elastics or a spring. Either elastic material or a spring. A spring, in some sense, it's more general because let's say the spring normally has this length. You can compress it, right? So this is the energy. So when you compress it, it'll have some energy and it's gonna want to expand it back to its what's called its equilibrium. And it's gonna want to expand it back. So it has some stored energy over here that's gonna transform into motion. It's going to change. If you put a box over here, it's going to push the box, right? So it's a box initially have no kinetic energy, but the energy over here is going to transfer to it and push it, okay? This, I don't need to leave it to the engineer. I know this is easy to imagine how it works. But it can be compressed. It can also be stretched. And in that case, it's going to want to pull it back, okay? So we actually have a formula for this. I'll just tell you as well. It's going to want to pull back to its equilibrium length, its equilibrium point. So if I attach a box over here, if I put some sticky tape, right, stick it around it, the spring is going to want to drag it back. So elastic material, usually we just talk about the pull, not necessarily the compression, but I guess you can talk about compression. So spring is basically the simplest type of elastic material, right? If you have rubber, you push it, so it's elastic, you push it. So now it's compressed, it will have energy to want to expand. If you stretch a rubber band, that's another example of an elastic material, it's going to want to restore back to its equilibrium. So a spring sort of, it's able to do both. So in physics, as you will see in 3C, you'll spend a lot of time in the first week or so looking at springs because it can deal with both and it's the same physics, right? And then we can approximate a lot of elastic materials like rubber bands as springs. So that is the strategy. We talked about this type of force associated with this as well. And as you will see, every type of energy, because it's a dual approach, it's really a duality, like a dual vision. You can look at things in terms of energy, you can look at things in terms of force. I've talked about the pros and cons of each. So in some sense, every energy sort of associates with a force. The electrical energy associates with the electric force. The elastic potential energy associates to a force as well, and it's the spring restoring force. We talked about that restoring force. And it's in terms of the restoring force, it's usually written like this: minus kx, like this. This is the force of the spring, right? Of the spring on the object. It's on an object. Usually it's that. What that means is x is the measurement, and let's be clear, that's a displacement technically. And displacement means the final position minus the initial position. Where's the x naught? Where's the initial position, x0? Usually we call it here. So if the final position is here, like this, right? You see, this is just 1D, so I can use plus and minus to define direction. What is is the displacement positive or negative if the spring is stretched to a final position over here, right? If I connect a box, right? If I take some sticky tape, wrap it around the spring, and I stretch it like this, the displacement is positive. I need to define my axis. So positive is this way. So xf minus x naught is going to be positive. If this is positive times this is called the spring constant. It's a positive number. It's always a positive number. It's always a positive number. The spring constant, it's 2, whatever, it just makes this number larger. So that's not going to change the sign. the force is going to be in the negative direction. So you see the restoring force, it's pointing this way if I draw a free body diagram of force, even though we're not talking about force in this chapter. But now when you compress it, so the final position is here, but when you take this, subtract this, the displacement is negative, right? If you have put it over here, now if this is a negative number, if this is 0, right, this is negative something, so negative minus 0 is negative. So the displacement, if it's negative, so this is displacement from equilibrium, just to be clear. I know this is part of 3C, but just to make your life in 3C easier, might as well. Displacement from equilibrium. Okay. So if the displacement from equilibrium is negative, you see that now the force will be positive. Okay, so that's why the free body diagram will have a force pushing it this way, and that's why we call it a restoring force. Okay, and there is, so technically you don't need to master the restoring force in 3A, but in the book we will use the energy of it. So I will need to talk about that. So the elastic energy or elastic potential energy is half K delta X squared, okay, like that. So a lot of times we call the equilibrium X equals to 0. So that then you will just see half K X squared, but this is more correct. I'll put that one in the box, right? K delta X squared. In case sometimes people like to make this 0, but yeah, if you make this 0, your life is easier, but where you put your origin doesn't affect the physics. Okay, so it's really a change in there, and that will be slightly easier, right? So if you want, you can put this ahead to make your life in 3C easier. Okay, the restoring force is half kx, sorry, minus kx. This is what you need to know for this course, all right? So that's the amount of energy stored in a spring. Let's put important formulas in the box. So that's okay. All right, so just a quick glance ahead, you can already kind of see how this would work, right? If I compress the spring like this by a certain displacement, and let's say I do know the spring constant is, let's say 2 in whatever appropriate SI units, or whatever the way I do it is, everything starts off with SI units, you don't have to worry about units anymore during the calculation. So let's say initially you start off with V equals to 0 initially, right? So now when it expands back to here, what will the energy be? So initially it has no, so you have elastic potential energy and kinetic energy, but initially you have no kinetic energy because you start off at rest. And at the end, again, if you only have these two types, right, there's no chemical energy going on, there's no electrical energy going on, there are other types I'll convince you there's nothing else going on. You have, when you go back to its equilibrium, what's the displacement from equilibrium? If you go back to the equilibrium, the displacement is 0, right? There's no more displacement. So you have no more elastic energy. So since energy cannot be destroyed or created, so all the elastic potential energy is going to transform into kinetic energy. And how much? Well, you can now calculate it, right? If you know half kx squared, if you know k is equal to 2, so if you buy a spring, they will tell you what the spring constant is. Just like when you buy a rope, it'll tell you what the tension, the maximum tension it can sustain. You buy a spring, it'll tell you the spring constant. You can basically measure the spring constant through experiments. If you take 3LA, the lab version of this course as well, you'll play with you'll see how we can measure these constants, the tension of the rope, the spring constant, etc. Anyway, yeah. So the easier version now, let's say we just read it off a label. You measure how much displacement. Initially, you compressed it. Let's say you compressed it for 0.5 meters. All right. So half a meter. All right. So half a meter squared. Whatever that number is, that's going to change its kinetic energy. And if you know the mass, you're going to calculate what is the final speed it is once the spring has pushed it from the compressed state back to its relaxed equilibrium state. Right. So that's already a quick glance ahead. Let's put it in brackets. I'll erase that in a second. Quick glance ahead how you can use energy, all right, to calculate, to predict motion. So now I can understand that without solving any Suvat equations, you see, right? So you see how potentially powerful this is. We'll look into it a little bit more. What other energies are there? So if I ask what other energies are there, I'm basically asking what other things can change an object's velocity, right? To change an object's kinetic energy. Remember, I define energy, right? Everything else as basically things that can change this. Well, electricity can change an object's kinetic energy. If you have something, if you have electrical energy in it, you can make it go faster or slower. If you have a spring, you can make it change its kinetic energy, right? So what other things can do it? So there are some less obvious ones. Yeah, but it's also reasonable the moment I say it. For example, heat energy. So this is anything. So it's the energy of temperature. So anything that has a temperature has heat energy, just like anything that has motion has kinetic energy. Anything that has chemical composition has chemical energy. Anything that's made out of electric fields has electrical energy. Anything that is a spring or elastic material has elastic potential energy. Anything have temperature has heat energy. You and I have heat energy. Now, do I have to worry about this thing? Probably have room temperature as well. Do I have to worry about that heat energy? You might ask. Well, let's see what happens if we do. Let's be complete. Like let's add up the heat energy as well. However, the temperature from the beginning and end, it's the same, right? So yeah, sure, but so it does have heat energy, but it cancels out on both sides. In essence, you have it, but the initial and final state is the same. So all the elastic potential energy is really just going into kinetic energy. Could it heat it up? Yes, it could potentially heat it up, but let's do the simple case. Let's do the simple case of, let's assume during this process, it doesn't heat it up. If you just imagine go into a lab, you push something, it will heat up a little bit, but that is what we call second order effect, right? Or second order, third order, fourth order. You have more important things to worry about other than the heat, the temperature being minutely, different. It's going to be like 0.1 degrees hotter or whatever. So that's not going to change things that much. So that's the reason why we didn't even need to worry about the other types of energy. You might say maybe there's some chemical in there, but again, it's not relevant to our process. Other types of energy is, for example, light energy. Light has energy. Okay, sound also has energy. Okay, so this is just the energy of light waves. You'll learn more about that in 3C as well. Energy of sound waves. You'll learn more about that in 3C as well. So anything that has sound, I am actually I'm speaking this sound energy. In fact, what's going on right now is how do I produce the sound is because I've ate lunch this morning. I should say afternoon. When I eat food, that's chemical energy that's stored in my body. And now I'm taking that stored chemical potential energy. Anything that's stored, if you see the word stored, by the way, you can call it potential energy. So I could call this electric potential energy, chemical potential energy, if you want to be more specific. So these are, you can, if you like classifications, most biologists love that. First thing you do is classify things. You can classify these as all different types of potential energy. If you want to draw a tree diagram and classify them, you can Google forms of energy or types of energy on Google, and then you can see different people can classify them. Because in this course, we're going to worry about two. I'm not going to worry too much about how you classify them. The two is sometimes classified into mechanical energy, but we'll talk about all those jargons. I'm not too worried about classifying that at this stage. Yeah, so back to sound wave is I've eaten stuff, so that's chemicals. So I've some chemical potential energy stored in my body. I'm taking that and transforming part of that energy into my muscles, which produce sound waves. Okay, so again, how does that do? As physicists, we leave the complicated stuff to other scientists. That's biology. So biology is extremely complicated. How you do that? How do you take food and create energy, like create your kinetic, you change it into kinetic energy of your diaphragm into your throat, and then your throat's vibration will create sound waves. All that is biology. We're just worried about, is it possible to transform? So if you do not eat enough food, you probably cannot produce sound waves. But it requires very little of energy to produce sound waves. So sound energy. So as long as you're alive, you're fine. Yeah. So what is the energy process going on? I eat food. There's chemical energy. Produce sound wave. There's sound energy. Now the sound energy goes into my microphone over here, and it changes the sound energy into electrical energy. So it stores that amount of electrical energy information. It actually stores pulses of electrical energy. So the computer now interprets that pulses turns that into electrical energy, but it's really pulses of electrical energy, and it's able to store that amount of information, pass it through the internet. Now you're watching this. Your computer is interpreting those spacing, those pulses of spacing, and it's transformed back into the kinetic energy of your speaker, of your computer's speaker. So the speaker will vibrate at a certain frequency to reproduce that pulse of those pulses of energy, and basically transforms the electrical energy into kinetic energy into sound waves. So into sound energy. The sound energy goes into your ears. The sound energy now makes your ear, what's that called again? I'm clearly not a biologist, as you can see. Yeah, whatever that organ is, just slipping my mind at the moment. It vibrates that, and then your brain can interpret that vibration, so it becomes kinetic energy again, just kinetic energy in a different place. It interprets that, and you now can hear what I'm saying. So it's really energy transferring all the way from my food into your ears, right? Sounds gross, but in terms of energy, it went through a lot of process step by step throughout there. But the amount of energy is always conserved throughout, okay? Now, is there wasted energy? Yes, because not all my sound energy went into the electrical energy, right? A lot of sound just went out and hit the walls. What will that do? Well, the walls actually absorb some of the sound energy. And what does it do? Well, the walls are made of atoms. So the atoms vibrate just a little bit more, and it heats up the walls just a tiny bit, right? Again, those are like, I don't know, 10th order effect. We don't have to worry about that. But I'll just consider those as sunk costs, those as just wasted energy. I really should do this, and now all the energy will, well, not all, but more energy will go in and not as much waste. But anyway, we're not here to worry about that. But yeah, you can see that sometimes you might say, hey, energy is not conserved because some of them is wasted. However, as a system in the whole universe, none of the energy is wasted. The wall is absorbing it. It's just a little bit hotter, right? And then when the whole wall cools down, it does something else. So energy as a whole system, inside a closed system, it's always conserved. Okay. In an open system, yes, energy can leave the system, but somewhere else takes it. Okay. Now let's add one or two more, depending on how you count it. And this is probably the more abstract one. Okay, but again, quite obvious once I say it, is gravitational potential energy. Okay, another form of potential energy, and this is what I call energy of height. Okay, if the object is located at a given height, it will have gravitational potential energy, GPE. Okay. And why is it obvious? Is because how am I defining energy again? Is the ability to change an object's kinetic energy, or ability to change an object's motion. Well, we already talked about that. If you drop a box, drop an apple, the fact that it has some height means it will be able to change its you release it, like not touch it anymore, it will automatically go from rest to going very fast. So it has changed its motion, it changes kinetic energy. So it must, over here, has more energy than here. What's the difference? The difference is height. So the fact that something is higher, it will automatically have more energy. So the black marker here has more energy than the green marker over here, right? The fact that it is just located higher, it will have more gravitational energy, okay? And if you think about, you might wonder, well, I thought energy cannot be created. Of course it cannot. The fact that I move it up here, I'm doing more work to pull it up here. I haven't defined work exactly, but you can imagine I need more chemical energy. More of my food is dedicated to push it up over here. Okay, so it's just another energy transfer. So I've transferred more energy by moving it up, but that's not going to get wasted, because if I let go, then all the gravitational potential energy it has, it's going to transform into kinetic energy, and it's going to be able to transform into more kinetic energy than an object at a lower height. Okay, so just like temperature, anything that has temperature has heat energy. It's just different amounts, right? The hotter it is, it's more heat energy. So this also tells you that heat is a form of energy. And I will give you one more that's related to this. It's the universal gravitational potential energy. It's because if I have an apple and an apple in space, right? Forget about the Earth. So just two apples in space. We've learned that due to Newton's gravitational law, he discovered that these two will just attract each other. All right. In fact, they attract each other with a very, very feeble force. If you, let's do a quick estimate of that, right? So probably should have done that in the last video. If I take these two apples with mass 1, mass 2, r square, and separate them by 1 meter, why don't we see this attraction in everyday life? Right? Have you thought about that? So we can do a quick estimate about that. Let's just do it quickly over here, right? What's M1? Well, apple weigh around 1 Newton, right? That's roughly a good reference point. So 1 Newton, if the weight is 1, what is the mass? Well, G is around 10, so mass better be 0.1, right? Or 1/10. So 1/10 times 10 will be 1. Okay, so we know that the mass is 0.1, so that's 10 to the minus 1 of the first apple. So the second apple in space is another 10 to the minus 1. And R, let's say I separate them by 1 meter, roughly from here to here, half of my whiteboard. It will be 1 squared, so that's easy to do. I almost don't need to worry about the denominator. What's G? In SI units, everything I'm changing, as you can see, to kilograms and meters. So everything is in SI units. That will make things easier. But G is around 10 to the minus 11. I think it's 6.67 times 10 to the minus 11, something like that. So if you multiply, so 1 is just 1, right? Multiply all that together, the force is around 10 to the minus 13 newtons, right? The force of an apple, the weight of an apple is 1 Newton. This is 0 with 13 zeros before you have a significant figure. I know it's going to 6.6 something, all right, 6 whatever. That's not going to change the fact that it's 13 zeros over here. So that's the reason why if you put two apples on the table, you don't see them like magnets and snap together. It's because whatever this universal gravitational force is that's pulling it together, the friction you have would be much, much more than this force. So it's not going to move. You have friction that's going to balance it out. Right? Right. Anyway, so that's just a quick detour. So you see how you can take the things you learn in this course and have useful conclusions in your life, understand why things happen or do not happen in this case. It's not the fact that you've disproved universal gravity, it's just friction exists. If you put it on completely frictionless place or put it in space, that force is so small that it will take, you can calculate what's the acceleration, right? If it's 10 to the, what did we say, minus 13 newtons of force, you need to divide by the mass, right? Mass times acceleration is the force. What's the mass of an apple again? 10 to the minus 1, right? So the acceleration is roughly 10 to the minus 12 meters per second square. So if you wait for 1 second, it's going to change the velocity from 0 to 10 to the minus 12 meters per second if you wait for 1 second, right? That's what acceleration means. It goes from 0 to 10 to the minus 12 in 1 second. So it's 10 to the minus 12 meters per second, right? You're not going to observe that. So that's why apples and apples, you know, they do attract each other. It's just extremely feeble. But when the mass is like 2 planets, or a planet and a moon or something like that, now we're talking. Now there's a measurable force, and you can measure that. Back to here is so just like we have a formula for gravity on Earth, and we have a formula for sort of the universal version, and we understand if you group this together, that's basically just G. So there's related in this sense. This is a special case from this. There is the more general one as well, which is universal gravitational potential energy. Okay. And yeah, we're not going to talk about that too much, maybe just a little bit, but mainly we'll focus on energy of height. And I have a formula for that. The gravitational potential energy, GPE, is mgh. So to summarize, we have 3 formulas we'll introduce, and I said there's only 2 things that is most important in this course, and it's going to be kinetic energy and the gravitational potential energy on Earth. If you want, you can put on in brackets on Earth like that. Okay, 80% of our study of energy is going to be worrying about how this transfers to this. Okay, we'll talk a little bit. So this formula is what you want to commit to memory. This formula is what you want to commit to memory. Okay, we'll talk a little bit about springs, but mostly that will be in 3C, but that's just in your textbook in this chapter. So we'll I'm putting this here. Okay, so these are the forms of energy there are. We are going to now look at a couple of conceptual examples, and we'll look at then some practical examples on actually predicting motion when this new light, in this new perspective of why things move.